GigaBrain 0.5M, a VLA that learns from world model-based reinforcement learning. This one is from the GigaBrain team at GigaAI, and it just dropped on February 13th, 2026.
Yeah, and this is a big one. We're talking about a vision language action system, a VLA, that fundamentally changes the game by integrating a world model directly with reinforcement learning.
And the dataset numbers are, frankly, a bit wild. They're pre-training on over 10,000 hours of data.
But here's the kicker.
6,000 of those hours are generated by the world model itself. Only 4,000 are from real robots.
Architecturally, they're using a SIGLIP encoder layer for vision. And for the decoder, a Gemma 2 decoder layer with expert.
Which points to a mixture of experts setup. And the results, they're serious. We're seeing a 10% success rate increase in box packing.
And a massive 20% increase in espresso preparation over the baselines.
So if you want to know how they used stochastic attention masking to prevent the model from, hallucinating, keep listening. Welcome back to AI Paper Podcasts. If you're tuning in, you're probably an ML engineer, maybe a researcher, or just someone trying to keep up with this fire hose of papers coming out in 2026.
And today's is a dense one.
It really is. I mean, the title alone, World Model-Based Reinforcement Learning, that sounds like the holy grail we've all been chasing for the last couple of years.
It kind of is.
So why does this paper, right now, matter so much?
Well, just think about the biggest bottleneck in robotics. It's not building the hardware anymore, it's teaching it. We have this huge sim-to-real gap.
Right. You can train something for 1,000,000 years in a perfect simulation, but the real world is messy. Physics gets weird, lighting changes.
Exactly. And you just can't run a physical robot for millions of trials. You'd be waiting a decade.
So what's the GigaBrain approach?
They're basically saying, we don't just need more data, we need a better way to generate feedback. They're using a world model, which is essentially a simulator learned directly from video, not just to predict what happens next.
But as the feedback mechanism for RL?
Precisely. They are manufacturing their own training signal on the fly.
And that explains that crazy beta split I mentioned. More synthetic data than real. Okay, but before we get into the data strategy, let's look under the hood. What's the actual architecture?
So it's a pretty classic VLA setup, but with, very modern components. For the eyes, the vision encoder, they're using the SIGLIP encoder layer.
SIGLIP? Yeah, that's been solid for a while. It tends to be more efficient than CLIP because it uses a sigmoid loss instead of a softmax, right? It just scales better.
Exactly. It handles the image-text alignment much better at scale, which is crucial when you're pumping high-res video frames into the system.
And for the brain, the part that handles language and action.
For that, they've gone with the Gemma 2 decoder layer with expert. And that with expert part is the key here. It tells us they're leveraging a mixture of experts approach.
Which is pretty standard now for keeping inference costs down while you blow up the parameter count. But I noticed in the specs they mentioned something called GigaTrain-1. Is that their own internal framework?
It is, and the specs are heavy duty. They train this with the batch size of 3,072.
3,000, that's massive. Usually for these kinds of complex multimodal tasks, you're seeing batch sizes in the low hundreds.
It's huge. And they ran it for 100,000 optimization steps.
Yeah.
But the detail that really caught my eye, and I think the engineers listening will appreciate this, is how they managed the memory.
Okay.
They used fully sharded data parallel V2, or FSDP V2.
Standard practice for big models. You shard the model states across your GPU so you don't run out of VRAM.
Yes, but here's the clever part. They applied it selectively. They sharded all of the SIGLIP encoder layer modules on the vision side. But for the Gemma 2 decoder, they only sharded the first 16 layers.
Wait, only the first 16? What? Stop there. Why not just shard the whole thing?
It's a really sharp memory optimization trick. See, by not sharding the later layers, they're probably balancing communication overhead against memory usage. FSDP has to do a lot of communicating between GPUs to reconstruct weights for the forward and backward pass.
Right. So if the later layers are where the mixture of experts routing is happening, maybe the communication cost of sharding those specific experts was just too high.
That's the likely inference, yeah.
Yeah.
It suggests the early layers of the MOE model are the memory hogs, parameter-wise, while the later layers are maybe more sparse or computationally lighter. It's a very specific, very clever engineering decision to squeeze every drop of performance out of their GPU cluster.
I love finding those little nuggets. It shows they really, really tune the infrastructure.
Okay, let's circle back to the data. 10,000 hours total.
Right. And of that, 4,000 hours is real robot collected data. This is your ground truth. The robot actually physically moving in the world.
And then the other 6,000 hours is this world model generated data. Correct. And this isn't just random video. They categorize it into specific buckets. Robot manipulation data, web video data, robot action, and this thing they call video state advantage.
Video state advantage. That sounds like where the RL part starts to creep in.
It is. The core insight here is that the robot can learn faster from its own imagination as long as that imagination is grounded in reality. They're generating synthetic trajectories.
Basically asking the world model, if I do this, what happens next?
Exactly. And then they train the policy on those simulated outcomes. It bridges the learning gap because you can generate those 6,000 hours infinitely faster than you can run a physical robot for 6,000 hours.
But that only works if the imagination is accurate, right? If the world model thinks throwing a cup makes it float back to the table, the robot learns total nonsense.
Precisely. And that leads us to the mathematical secret sauce of this paper.
Yeah.
This is where it gets really interesting for the RL folks out there.
Okay, lay it on us.
So they're doing world model-based RL. The core equation involves estimating a policy, standard stuff. But the update rule relies on this exponential advantage term, XPV.
I see the beta term in there. That's like a temperature parameter.
Essentially, yeah. The problem is that exponential term, if the advantage A gets too big or it fluctuates, that term just blows up.
Numerical instability.
Totally. Your gradients explode, the model collapses. You can't just plug that into PyTorch and hit run.
So how did they fix it?
They did something really clever. They introduced a binary improvement indicator. Let's just call it I.
Okay, simple enough. Did it get better? Yes or no? 1 or 0?
Right. But then, and this is the key, they apply Bayes' theorem. They reformulate the probability of observing an improvement, P on ES, to be proportional to that nasty exponential advantage term.
Oh, I think I see what they did. So they turned a regression problem predicting the exact value of the advantage into a classification proxy.
You got it. By effectively just asking, what is the probability that this action leads to an improvement, Koji? They stabilize the entire learning process. Probabilities are neatly bounded between 0 and 1. Exponentials are not. It creates a dense reward signal that doesn't blow up your loss function.
That is slick. And they have that figure in the paper, figure 13, that shows this in action, right? The laundry folding scenario.
Yes, that visualization is fantastic. So you see the robot trying to fold a piece of clothing. And in the video feed, there is a green garment that accidentally gets in the way of the fold.
A classic laundry disaster. I know it well.
Right. And if you look at the graph of the predicted value, the robot's internal confidence of success, it just tanks. There's an orange bounding box highlighting this value drop.
Yeah.
The model realizes, uh-oh, something is wrong. This green thing should not be here.
It knows it's failing in real time.
Yes. But the manipulator moves, it removes the obstruction, and you see the blue line on the graph shoot back up. The value recovers. This proves the world model isn't just, imagining a happy ending. It understands state dynamics. It gets that obstruction equals failure and removal equals recovery.
That brings up the elephant in the room, though. You mentioned hallucination in the intro. If we're relying so heavily on a world model, what happens if the model imagines something that isn't there? Or misses something that is?
This is the fundamental danger of model-based RL. If your world model is wrong, your policy just learns to exploit the bugs in your model. It's like reward hacking in a simulation.
So how does GigaBrain stop the robot from learning to chase ghosts?
They use two specific strategies for robustness. The first one is a training technique called stochastic attention masking.
Masking, like in BERT.
A similar concept, yeah. But they apply it to the world model tokens. During training, they randomly suppress or mask out tokens from the world model with a probability of 0.2.
So 20% of the time, the policy literally can't see what the world model is predicting.
Exactly. It forces the policy to not become over-reliant on the world model. It's like training a pilot to fly by instruments, but then you randomly turn off their GPS. You force them to look out the window.
So it has to rely on the raw vision encoder and its own internal state.
It makes the policy robust to those moments when the world model might be confused or just unavailable. It's basically a dropout layer for the world model itself.
That makes a ton of sense. And the second strategy?
That one's for inference speed. When they actually run this on the robot, the world model performs only a single denoising step.
Just one. Usually diffusion models or these generative models take dozens, sometimes hundreds of steps to get a clear output.
Correct. But in a real-time control loop, you don't have time to wait 500 milliseconds for perfect prediction of the next frame. You need an answer now. By limiting it to a single denoising step, they minimize the computational overhead. It's a trade-off.
A slightly noisier prediction that's delivered instantly is better than a perfect prediction delivered too late.
Speed is life in robotics.
Absolutely. Okay, let's talk about the hardware. They didn't just run this in a sim.
No, they deployed on real metal. They validated this on Piper arms, specifically for a task involving paper tail preparation.
And the G1 humanoid robot.
Yeah, the G1, which is the unitary humanoid, they use it for a table bussing task.
Bussing tables with a humanoid is bold. That requires both mobility and manipulation in a pretty unstructured environment.
That's a great test case. So the main tasks they benchmarked were paper towel preparation, table bussing, box packing, espresso preparation, and laundry folding.
Espresso preparation, that sounds incredibly delicate.
It is. I mean, think about the precision you need to insert a portafilter or tamp the coffee grounds.
Yep.
And this is where the results get really impressive. Compared to their reference policy, GigaBrain-0.5 got a 20% increase in success rate for espresso preparation.
20% on a fine motor task like that. That is not statistical noise.
No, it's significant. And for box packing, which is more about spatial reasoning, they saw a 10% improvement.
They also mentioned improvements in highly dexterous tasks.
Right. They highlighted things like hanging a paper towel, which involves deformable objects. Handling soft, floppy things is notoriously hard for robots because the state space is basically infinite. A rigid box is a box. A towel is a mess.
The fact that they showed improvements there really validates the whole world model approach. The model can predict how the towel will flop better than a simple geometric formula ever could.
That's the idea.
How are they actually measuring prediction quality? I saw a bunch of acronyms in the evaluation section.
They used a validation set of about 1 million frames. The metrics were MAE, MSE, and RMSE. Mean absolute error, mean squared error, root mean squared error. For those, lower is better. You want your prediction to be close to the pixel reality.
Standard regression stuff.
But they also use Kendall's tau.
Remind me what that one captures.
Kendall's tau measures rank correlation. And in this context, it's crucial. It answers the question, if the model thinks state A is better than state B, is state A actually better in reality?
Ah, I see.
Even if the pixel-perfect prediction is a little off, if the ranking of potential futures is correct, the RL agent will still make the right decision. For Kendall's tau, higher is better.
That's a great distinction. The robot doesn't need to hallucinate a 4K photorealistic image of the future.
No.
It just needs to know that action A leads to a better future than action B.
Exactly. It's about decision utility, not just image generation.
So to bring it all together, we have a VLA that's using a selectively sharded MoE architecture. It's training on a massive dataset that's mostly hallucinated but grounded futures. It stabilizes the RL with a clever Bayes theorem trick, and it blinds itself 20% of the time during training just to stay tough.
And it makes a better espresso than the last version.
That's the summary, but I think the implication here is even bigger. Well, look at the trajectory. We have a model generating 6,000 hours of training data today. That's a 1.5 to 1 ratio of synthetic to real data. What happens when the compute gets better and it can generate 600,000 hours?
You're asking if we're reaching a point where the robot learns primarily from its own imagination rather than physical reality.
I think so. If the world model becomes accurate enough, then physical data is just the seed. It's the calibration set, the actual bulk of the learning, the millions and millions of repetitions. It all happens inside the model's mind.
We might be looking at the beginning of the end for the data bottleneck in robotics.
That is a wild thought. We're moving from learning from demonstration to learning from contemplation.
In a way, yeah.
And if you want to see what learning from contemplation actually looks like, specifically the videos of that G1 humanoid bussing tables, which is just cool to watch, you have to check out the project page.
It's at gigabrain05meet.github.io. The videos of the laundry folding value drop are also there, and they really help visualize the math we were just talking about.
Definitely check that out. For all the engineers listening, hopefully this gave you some ideas for your own sharding strategies or maybe your RL loss functions.
And always check your batch sizes.
Always. Thanks for diving in with us. Keep training.